Now, the sixth video on the topological spaces, we're still dealing with the second subsection after the mathematical foundations that saw us going through the first four videos. Now, starting from the last video, we started this subsection under the playlist again, which is visual and intuitive topology. And it's just like I said in the last video, it's all about introducing ourselves to the general concepts of topology before we even start going into the serious mathematics that topology is about. So here it is just us building ideas about the visuals and the intuition behind topology. And in this video, we're looking at famous spaces. So if you like, famous topological spaces. So which are the famous spaces we study in this place? I mean, in the last video, we already began to see things like circles, ellipses, and all of this. So let's see what we have here. So, topology becomes much more concrete when we study specific spaces that appear repeatedly throughout mathematics. In this lesson, we examine eight important examples. That does not mean that that's all we have. That's all there are as far as topological spaces are concerned. So, in this lesson, we examine eight important examples. We have circle, sphere, torus. We talked about these three in the last video for sure. Then Mobius strip, Klein bottle, projective plane, cylinder, and cone. So these spaces are important because they illustrate fundamental topological ideas such as connectedness, compactness, boundary, orientability, holes, continuous deformation. I mean, we came across some of these concepts in the last video also. Quotient constructions, embeddings, and topological equivalence. I mean, we talked about topological equivalence a lot in the last video, so where we came up with the idea of homeomorphism, that uh, two spaces are homomorphic if the function mapping them together is bijective. It is the inverse the function is continuous and its inverse is also continuous. Then the central question is not simply what does the space look like. Instead, topology asks what properties of the space remain unchanged under continuous deformation. And we also agree that that continuous that deformation is something like bending, stretching, compression, twisting, which are allowed topological actions. But so things like tearing and gluing are not allowed as topological action. So let's see why do we have to why do we have to study these famous spaces? A topological space can be studied abstractly from its definition, but concrete example make the theory easier to understand. The spaces in this lesson serve as standard models. For instance, the circle is the simplest closed one-dimensional manifold. So you see the circle here. It is the simplest closed one-dimensional manifold, as you can see. Then the sphere is the fundamental example of a closed two-dimensional manifold with holes, like what you can see here. So it is like a circle in three dimensions. Then you have the torus, which has one handle and provides the simplest example of a closed orientable surface with a non-trivial fundamental group. So you have the torus here, like with so it's more like a sphere with a hole in it, but then and then so it's sphere that is punctured and then taped inside, something like that. So you have a torus there. So a torus has one handle and continue and provides the simplest example of closed orientable surface with a non-trivial fundamental group. Then you have the Mobius strip, this, which is a surface with boundary that is non-orientable, like that. So so this is orientable, this is non-orientable. So this can really get confusing. You're looking at what exactly, how does it really come out, right? Then you have the Klein bottle, which is a closed non-orientable surface. So this is a Klein bottle also. So it's a closed non-orientable surface like that. Then you have the projective plane, as you see here. So the projective plane is another fundamental closed non-orientable surface, which is this now. So projective plane, RP squared, circle S1, sphere S2, torus T2, like that. Then you have the cylinder, which is a surface with two boundary components. So you have a surface with two boundary components. I suspect that should be the radi this that the circle up here and the circle down here. Those are the boundaries. So the cylinder is a surface with two boundary components. Then you have the cone, which illustrates how collapsing an entire boundary to a single point can change the topology. So it's more like, so the cone is just like the cylinder, except that one of the top has been collapsed into itself. So it's illustrating how collapsing an entire boundary to a single point can change the topology like that. So These are famous topological spaces to study. So learning these spaces provides a vocabulary for discussing much more complicated topological objects, as we can see. So these are famous topological spaces that helps us. So all shapes, what we have here, all shapes are shown with grids to illustrate their surfaces. So some claim bottle projective plane are visualized using standard 3D models that help convey their structure, basically. So that these are famous topological spaces like that. Now, let's talk about a circle. We'll pick them one after the other. The circle is one of the most fundamental spaces in topology. For a radius r greater than 0, the circle centered at the origin is S1, which is the collection of all xy, which are real, such that x squared plus y squared is equal to r squared. This is the standard equation of a circle passing through the origin. So for the unit circle, r equals 1. So we have S1 to be xy belonging to r squared, and x squared plus y squared is equal to 1. So a convenient parameterization is gamma of t, which is cos theta, cos t sine t, where t lies between 0 and 2 pi. And notice that y of 0 is equal to y of 2 pi, right? So it means that the continuous transformation here, like what we saw in the last video, so the shape in the beginning is the shape in the end. So as you go on with the continuous transformation of a circle, so gamma of 0 is equal to gamma of 2 pi. Thus, the parameter interval has its two endpoints identified like that. So let's look at the topological properties of the circle. So the circle has several important properties. First of all is the connectedness. The circle is connected. In fact, it is path connected because any 2 points on the circle can be joined by a continuous path line entirely on the circle. So for any circle, mark any 2 points on the circle. You can draw any line along the circle to join these two points. Then there's compactness. The circle is compact because it is a closed and bounded subset of R squared. So it is a closed and bounded subset of R squared. So the area is bounded in between like that. Then there's no boundary. As a one-dimensional manifold, the circle has no boundary. Locally, every point looks like an open interval. So every point inside the circle looks like an open interval. Then it is one-dimensional. The circle is a one-dimensional manifold, even though it is embedded in the two-dimensional plane. Then it has one hole. Informally, the circle has one central hole. This intuition becomes mathematically precise through invariants such as the fundamental group and homology. So its fundamental group is pi sub 1 S1 being homeomorphic to Z. That's the set of integers. So the integer records how many times a loop winds around the circle like this. Then we talk about winding around a circle now. Consider the loop gamma of t, which is cos 2 pi t sine 2 pi t for 0 for t line for taking values from 0 to 1. At t equals 0, right? You have gamma of 0, which is cos 0, that's 1, sine 0, that's 1. Because when you put t here, 2 pi times 0, that's 2 pi multiplied by 0, that's 0. So cos 0 is 1. Then 2 pi times 0, that's 0. Sine 0 is 0. So at t equals 1, you have cos 2 pi, at t equals this cos 2 pi, that's cos 0, which is 1, and sine 2 pi is 0. Therefore, the path starts and ends at the same point. That's winding around the circle now. So the path starts and ends at the same point, and that's one interesting property of a circle that we saw from here. That where did we see that now? Yeah, okay, the one hole issue, right? So the path is like that. So therefore the path starts and ends at the same point. During the journey, however, the point makes exactly one complete revolution around the circle. So the corresponding winding number is 1. Now consider if we have gamma of t is cos 4 pi t sine 4 pi t. This path makes two complete revolutions to its winding. So this path makes two complete revolutions. So its winding is 2, 4 pi t. So similarly, y gamma of t rather cos minus 2 pi sine minus 2 pi has winding number -1. This illustrates why pi 1 of S1 is homomorphic to the set of integers. So each loop can be classified by an integer winding number. So each loop uh, can be classified as an integer winding number like that, depending on how that is demonstrated. So how do we visualize the circle now? So we take the x-axis to be cos t, the y-axis is sine t, and then t is from 0 to 2 pi, that's 360 degrees. Then we plot x against y, and then we end up having this circle here. So this is a point along the circle. So if you, like we said, if we put any 2 points along the circle, so there's a line along that circle to join it, and that talks about the connectedness of a circle like that. So with that out of the way, then we can go ahead to talk about a sphere. A sphere is a circle in 3D, if you like. So the two-dimensional sphere is denoted by s squared. So the unit sphere is S2, which is the collection of all x, y, z belonging to the three-dimensional real number space, which is x squared plus y squared plus z squared equals 1. More generally, a sphere of radius r is x squared plus y squared plus z squared equals r squared. So it's just like the equation of a circle, except that you have a third dimension here. So this is 3D and the circle is 2D. So the sphere is a two-dimensional surface embedded in three-dimensional Euclidean space. So this distinction is important. The sphere is not a three-dimensional solid. So the surface itself is two-dimensional because locally a small neighborhood for any point looks like an open disk in R squared, like that. So it's more like a circle in 3D, like that. So topological properties of the sphere. The sphere has the following properties. It is connected. S squared is connected and path connected, just like the case of a circle. Any if mark any 2 points on the sphere and you have a line along the sphere that can join it together. Then it is compact in that S squared is compact because it is closed and bounded in R cube. So the volume is bounded in there. So no boundary. The sphere has no boundary also. It is orientable. The sphere is orientable. Informally, one can consistently distinguish an outside from an inside in the sphere. So that's the idea of orientability, which we are still going to see as we move on. Then it is simply connected. Every loop on the sphere can be continuously contracted to a point. Therefore, pi sub 1 of s squared is actually e. That is the identity element or so. So this makes the sphere fundamentally different from the circle. So for the circle, right, it was you can map to the number of to integers. So for the circle, pi 1 s1 is can be mapped to the integer system of integers, while for the sphere, pi 1 s squared is simply 0, the identity element there. So example, talking about a great circle, in geography, we get to talk about the great circle distance along the earth, and all of that when we talk about latitude and longitudes. Consider the unit sphere, x squared plus y squared plus z squared equals 1. The intersection with the plane z equals 0. When z is 0 here, it becomes a circle with radius 1. Therefore, the intersection is a circle basically. So a parameterization is gamma of t is cos t sine t, comma 0. This is called a great circle because its radius equals the radius of the sphere. So great circles are important because they provide natural closed curves on the sphere. However, unlike a loop around the central hole of a torus, a loop around the sphere can always be contracted to a point. This is one of the key topological differences between S2 and a torus. That is between a sphere and a torus. So a geometric quantity, which is the surface area now, although topology does not depend on measurements such as area, geometric quantity can still help us understand the space. For a sphere of radius r, the surface area is a, which is 4 pi r squared. For the unit sphere now, a is 4 pi. So because the unit sphere has radius 1, so the area is then 4 pi. The important topological point is that changing the radius does not change the topology. So a sphere of radius 1, radius 10, or radius 100 is topologically equivalent to every other sphere. So the size changes and the topology does not, like that. So we can represent a sphere using this whole Python code right here. So this is us declaring u here. We have from 0 to 2, v 0 to pi, and then for the x now, we have the radius, the outer cos u sine v, then y. So u and v are defined here, and then they are used inside here. And for z radius now, we have np ones like u and cos v like that, and then we run this whole code, and we get the sphere this way. Now let's talk about the torus. A torus is the familiar shape of a donut. So remember the torus I showed initially. It's what looks like a donut like this. So that's what a torus is like. So a torus is the familiar shape of a donut. A standard torus embedded in R3 can be parameterized by XUV, which is big R plus small r cos V cos U, then big R plus small r cos V multiplied by sine U, and then R sine V, where U and V lie between 0 to 2 pi, between 0 and 360 degrees. And big R is bigger than small r, which is bigger than 0. Here, R is the major radius Big R is the major radius and small r is the minor radius. The torus is a two-dimensional surface embedded in three-dimensional space, just like a sphere. But two fundamental loops on the torus now. The torus contains two fundamentally different types of loops. It has a meridional loop. A meridian goes around the short circular direction of the tube, so you can fix U to be equal to U naught and vary V. Then you have the longitudinal loop. So a longitudinal loop goes around the large central hole. So fix V equals V naught and vary U. So these loops cannot generally be continuously deformed into one another. So they represent two independent directions around the torus. Consequently, pi one of a torus is actually homomorphic to a two-dimensional integer space. So a loop can therefore be characterized by two integer winding numbers. So it's like for a circle, it's one integer winding number, but then for a torus, it's two integer winding numbers because it's like we are dealing with two circumferences. Like if you look at this torus right here now, so the first one is, you have the meridional, which is around the thickness of the circle, but the longitudinal is around like that, and that is why you have that two-dimensional thing we have in this case. Okay, so this is another example of a torus here. So, but before we get to that, right? Um, Okay, a loop can therefore be characterized by two integer winding numbers for a torus. So consider the torus parameterization XUV, which is RR cos V cos U, R plus R cos V cos U, R plus R cos V sin U, R sin V. So fix V to be 0. When V is 0, right? So you have cos 0 is 1. So you have R plus R cos U here. And then R cos V is also 1. So you have R plus R sin U. Then V is 0. So goes to 0. As U goes from 0 to 2 pi, the point travels once around the large central direction. Now, if you fix U to be 0, then x of 0 V, that means cos 0 is 1. So you just have R plus R cos V. But in this case, sine 0 is 0. So everything here goes to 0. And then here there's no U. So you just have R sine V. So as V goes from 0 to 2 pi, the point travels once round the tube. So this is traveling around the tube. These are two different fundamental directions. So a loop with winding numbers m, comma n, wind m times in one direction and n times in the other. And this is how we can represent a torus using a Python code. So we define all those things we saw up there. So you define U, which is 0 to 360 degrees, V 0 to 360 degrees. And then, of course, if you take big radius to be 2 and small radius to be 0.8, and then we have the UV, which defines the mesh grid. So we have our XYZ now, and we define all this big R plus small r times cosine of V, which has been defined there, and cos U like that. So by the time we run this, now we get the torus. So you have the torus here. And just like what we said the other time, so there's movement round around the shape like this, and there's also movement inside, so across this length like that. So meridional and longitudinal movement. That's why we have it. We have two winding integer numbers like that. Then let's go to the Mobius strip. So the Mobius strip is one of the most famous examples in topology. It can be constructed by taking a rectangular strip, giving it a half twist, and joining the two ends. That's what like a Mobius strip looks like. Again, this is the original shape we have here. This is a Mobius strip right here in focus. So it's more like you have this shape going and then you turn it over and tape it together. That's how to create a Mobius strip. So it can be constructed by taking a rectangular strip, giving it a half twist, and joining the two ends. A parameterization is x of u comma v, which is 1 plus v over 2 cos u over 2 cos u, 1 plus v over 2 cos u over u. So this one looks a bit like torus, except that you have the fractional parts now, and the multiplications you have inside here. And you have u is from 0 to 2 pi, and v is from -1 to 1. So the identification at the ends introduces the half twist. So you have the half twist thing going, and then the Mobius strip has only one side. So the Mobius strip is non-orientable. So this means that there's no globally consistent way to choose one side as front and the other as back. So imagine placing a small arrow on the surface and pointing continuously around are moving continuously around the strip. After one complete journey, the arrow returns reversed. So this cannot happen on an ordinary cylinder. So the Mobius strip also has only one boundary component. So this is surprising because a rectangular strip appears to have two long edges. So after the ends are joined with a half twist, those edges become one continuous boundary curve. So example, if we trace the surface, imagine drawing a line across the center of a Mobius strip. Start at a point on the center, then move continuously around the strip. After one full revolution, you return to the starting location. However, the local orientation would have been reversed in that case. So if you continue for another revolution, the orientation returns to its original state. So this provides an intuitive demonstration of non-orientability. An ordinary cylinder behaves differently. Going once around the cylinder does not reverse the orientation. So we have the Python visualizing of Mobius strip using all the formulas we have up there. We have all of that here. And when you run that, you have the Mobius strip like this. So it's like this doesn't really do so much justice to it, but something like this. Then we have the Klein bottle. If you remember the Klein bottle, this is it right here. Yeah, this guy. This is a Klein bottle here. So it's a closed, non-orientable space also. So you can't really distinguish inside and outside or this or that. So coming to that here, the Klein bottle is a closed, non-orientable surface. It can be constructed conceptually from a rectangle by identifying opposite edges with different orientations. One pair of opposite edges is identified in the same direction, while the other pair is identified in opposite one pair of opposite edges is identified in the same direction, while the other pair is identified in opposite directions. Symbolically, a rectangle can be represented as 0 by 1 multiplied by 0 by 1, and the identifications are 0, comma y to 1 comma y, and x comma 0 to 1 minus x comma 1. So these identifications produce a Klein bottle. So why is the Klein bottle strange? A Klein bottle has several remarkable properties. It is connected, it is compact, it has no boundary, it is non-orientable, it is a two-dimensional manifold. Unlike the sphere and torus, the Klein bottle cannot be embedded in ordinary three-dimensional Euclidean space without self-intersection. So a familiar three-dimensional picture of a Klein bottle therefore appears to pass through itself. So this apparent intersection is not an intrinsic intersection of the abstract surface. It occurs because we are trying to represent a surface that naturally requires four-dimensional space for an embedding. Thus, the apparent crossing in the usual picture is an artifact of the three-dimensional visualization. Yes, I was trying to remember this when I was teaching on one of the videos on the mathematics of artificial intelligence. Now, when we just started having generative AI, so all the time that maybe you create a man, and the man ends up having three hands or seven fingers, things like that. These are called those extra fingers, or that strange behavior is what you call artifacts. I was trying to remember it in one subsequent video, but after the original, I didn't remember. So that's the idea of artifacts. So the Klein bottle has a quotient space now. The Klein bottle provides an important example of a quotient construction. So if you start with a square, identify the length and right edges in the same direction, then identify the top and bottom edges in opposite directions. The resulting quotient space is the Klein bottle. So this idea is fundamental in topology. So instead of constructing a complicated surface directly, we can construct it by taking a simple object and specifying which points should be regarded as identical. So this approach also produces the torus, cylinder, Mobius strip, and projective plane. So using all these formulas here, we can generate the Klein bottle. So we have the Klein bottle like this. So I think this even gives a better picture than what the original one we have, but that one was just trying to, give us the best as possible. But this is more like it, what a Klein bottle looks like. Then let's go to talk about a projective plane. So it's some kind of disk looking thing like that. So the real projective plane is denoted by RP squared. One definition is RP squared is R cubed, take away so three-dimensional real number system, take away zero. And then this is where x goes to y whenever y is lambda x for some non-zero real number x. In other words, two non-zero vectors represent the same point of projective space if they lie on the same line through the origin. Therefore, x approaches minus x. So this identification is the key idea behind the projective plane. So just for reminder, this is what a projective plane looks like. It looks like this. three-dimensional disk, but with a thin width like that. Of course, a cylinder, I may not have to come back for cylinder because it's cylinder and cone are well known to us. So, still talking about the projective plane, we have. So the resulting quotient space is the real projective plane. So this construction is extremely useful because it turns an abstract algebraic definition into a geometric one. So the projective plane is compact, connected, boundaryless, non-orientable, and two-dimensional. It cannot be embedded in R3 without self-intersection, as we like that. Then we have fundamental group now. So the projective plane has fundamental group, that is pi 1 of RP squared is homomorphic to Z2. Z2 contains 0, 1, 0, 1, yeah? Yeah, Z2 contains 0, 1. So this means that loops have two essential classes. One class is represented by a contractible loop. The other represents the non-trivial elements. So 0, 1 like that. So if the non-trivial loop is traversed twice, it becomes contractible. Symbolically, if A represents the non-trivial loop, then A squared is equal to E. This is fundamentally different from the circle where pi 1 of S1 is actually Z. So for the circle, no positive number of non-zero windings becomes trivial. So for the projective plane, two copies of the basic non-trivial loop become trivial like that. So then we come to cylinder. A cylinder can be viewed topologically as S1 by 0, 1. So it's more like you have the circle, but then you now have a height to it like that. So it's more like you have a circle together with a height. So where S1 represents the circular direction, while 0, 1 represents the vertical direction. So a parameterization of a unit cylinder will be x of theta by z, comma z is cos theta sine theta z, where theta lies between 0 to pi and z lies between 0 and 1. So the cylinder has two boundary components, the bottom circle and the top circle. These are the boundary components. Therefore, unlike the sphere and torus, the cylinder has a non-empty boundary. So it has a non-empty boundary like that. So cylinder versus torus. So we can now let's begin to compare. So the cylinder and torus may look somewhat similar because both contain circular directions. However, they are topologically different. The cylinder has boundary, the torus has no boundary. So the boundaries of a cylinder are the top and bottom circles, as we know, but the torus has no boundary. So the cylinder, which is circle and height, while the torus is circle and circle. So the interval 0, 1 has endpoints, the circle S1 has no endpoints. So therefore, replacing the interval direction of a cylinder with another circle removes the boundary and produces a torus. If you replace the interval direction of a cylinder with another circle, with another circle removes the boundary and produces a torus like that. So let's talk about from cylinder to torus. How do we transform from a cylinder to torus? Start with a cylinder, which is the combination of a circle and a height. Its boundary consists of S1 and 0 and S1 and 1. So now identify these two boundary circles point for point. The interval direction becomes circular, thus S1 by 0, 1, take away X naught going to X1 is homeomorphic to S1 by S1. Therefore, gluing the two boundary circles of a cylinder together produces a torus like that. So we have the cylinder now. So you have this cylinder. These are to generate that. Just we have the theta, the angle, we have z also, and then theta z mesh grid. So cos theta sine theta. So you have circle and height coming together basically there, and we run that and we get the cylinder right here. Then of course we have the cone, the space that is cone. A cone can be constructed by taking a circle and connecting every point on the circle to a single point called the apex. So of course that's easy to imagine. Especially I talked a lot about cones when we dealt with circles, areas, and volumes, length, areas, and volumes. So it's more like you have a circle down here. They just make sure every point emerge from here and end in that point like this. So that's what a cone looks like there. So a simple parameterization is x of r comma theta equals 1 minus r cos theta, 1 minus r sin theta, then r, where r lies between from 0 to 1, and theta is from 0 to 2 pi, where when r is 0, you have x of 0 comma theta, which is cos theta sin theta 0, which gives the circular base. When r is 1, you have x1 theta, which is 0, 0, 1 for every theta. Thus, the entire circle at r equals 1 collapses to one point, which is the apex. Then the cone as a quotient space. The cone can be constructed from a cylinder like uh, from a cylinder-like space by collapsing one boundary circle to a single point. Starting with S1 and the height, we collapse S11 to 1 point. So the resulting quotient is now a cone. Symbolically, C of S1 is S1 by the height slash S1 by 1 collapse to a point. This is an important example of a quotient construction. So the operation changes an entire circle into 1 point. So in fact, one way I teach cone when I'm teaching conic sections is, a cone is like one third of a cylinder. So you have a cylinder this way, have a cylinder this way, and then imagine you have a point here. So try to connect this line with this line with this, and this with that. So you end up having like, in fact, by the definition of the formula of a cone, it looks like the volume of a cylinder is pi r squared height. But that's volume of cylinder, but volume of a cone is what? 1 over 3 pi r squared height. So it's more like from a cylinder, you get three cones functionally like that. So that's how you can create a cone from a cylinder. So the operation changes an entire circle just into one point. Now let's talk about topological significance. The cone is especially important because it is contractible. Every point of the cone can be continuously moved toward the apex. Therefore, every loop in the cone can be contracted to a point. Hence, pi 1 CS1 is E. This is a useful comparison. So the circle has pi 1 S1 leading to, which is now homomorphic with the integer system, but its cone has pi 1 CS1, which is E. So just the quotient construction can dramatically change the topology of a space. And then we have the visualization, like what we have here now. So Python visualization of a cone, import numpy as np, then import matplotlib.pyplot as plt. Then we have theta, you have 0 to 360 degrees, then r is from 0 to 1. Then you have theta and r for the mesh grid. So you then have 1 minus r cos theta, 1 minus r cos theta. So we put all of that together and we get our cone like this. So it's more like, you have a cylinder and then you collapse the circle into just a single point up there. Talking about that contraction we came across. So in this case now we have we want to compare the famous spaces here. We see that for a circle which is S1, it is one dimensional, and the boundary, no boundary, it's orientable, it's compact. The fundamental group is integer, the integer group. Then you have the sphere S2, two-dimensional, no boundary, orientable, compact, and trivial. So it goes to that zero now. That's the collection of that E. Then torus T squared, two-dimensional, no boundary, orientable, compact, Z by Z. Mobius strip, two-dimensional, one component boundary, then it's not orientable, it's compact, and then the fundamental group is integer. Therefore, the Klein bottle, two-dimensional, no boundary, it is not orientable, it is compact, and then the fundamental group is AB such that A inverse is B inverse. Then you have projective plane RP squared, two-dimensional, no boundary, not orientable, compact, and fundamental group is Z2 containing just 0 and 1. Then you have the cylinder, two-dimensional. The boundary is two components, the top circle and the bottom circle. And it is orientable, yes. It is compact, of course, yes. Fundamental group is integer. Then coming to cone now, the cone is two-dimensional. It has one boundary component, which, in a cone, in a cylinder, yeah, there are two circles. In a cone, there's one circle. That base circle is now like the boundary. So that's one component. Orientable, yes. It's compact, of course, and fundamental group is trivial, just like the case of a sphere. So the table illustrates why topology needs more than visual appearance. So visual appearance is not enough. Two spaces can have similar geometric appearances, but different topological properties. For example, cylinder versus torus, boundary distinguishes them. Cylinder has two boundaries. Cylinder versus Mobius strip, orientability distinguishes them. So sphere versus torus, fundamental group and holes distinguish them. Then projective plane versus sphere, orientability and fundamental group distinguish them like that. So I mean the table summarizes all of that. So projective plane and sphere, for instance. So you see sphere, projective plane. So they are both two-dimensional for sure. But then the boundaries, they also have no boundaries. Orientable sphere is orientable, but Projective plane is not orientable. They are both compact, and then fundamental group makes the difference. Sphere has the trivial and orient fundamental group, while a projective plane has Z2 as its fundamental group like that. So then we'll talk about the idea of boundary. So the boundary of a manifold consists of 2 points whose neighborhoods resemble a half disk rather than a full disk. For example, in this lesson, S1 has no boundary, but then S2 has boundary. So circle has no boundary, sphere has no boundary, the torus has no boundary also. The Mobius strip has one boundary element, the Klein bottle has no boundary, RP squared has no boundary, the cylinder has two boundary elements, the top and bottom circles, the code has one boundary component, which is the base base circle, right? Boundary provides a powerful way to distinguish spaces. For example, a cylinder cannot be homeomorphic to a torus because one has boundary and the other does not. So for them to be homeomorphic or topologically equivalent, they have to have the same kind of characteristics. Then we talk about orientability. Orientability asks whether a consistent notion of local orientation can be chosen through the entire space. The following spaces are orientable. Circle, sphere, torus, cylinder, and cone are orientable, but the following are non-orientable. Mobius strip, Klein bottle, and projective plane. I mean, the popular ones are orientable, including torus, but these ones that are not so popular are not, they are not orientable. So the Mobius strip is the simplest and most intuitive example of non-orientability. Its half twists prevents a globally consistent orientation. So it should have really been like a ring or something like that. But because you now have a flip over and taping kind of thing, then it becomes like it becomes inconsistent in that way. Then we talk about compactness as another characteristic of topological of the kind of features of topological spaces. All eight spaces considered here are compact when considered with their standard topologies. Compactness is a topological generalization of the idea of being closed and bounded in Euclidean space. And we know the idea of being closed and bounded, which we have studied in earlier videos. Then for subsets of R for n-dimensional real number system, right? The Hahn-Borel theorem states that a set is compact if and only if it is closed and bounded. However, compactness is more general than this characterization. For example, the abstract Klein bottle is compact even though its familiar three-dimensional visualization contains an apparent self-intersection. You know, I think we saw that here. There's a kind of self-intersection when we talk about a torus. Yeah, this Klein bottle, is it? Yeah, I think it's Klein bottle that has self-intersection, right? So, despite the apparent, yeah, it's Klein bottle, right? That though it's familiar three-dimensional visualization contains an apparent self-intersection. That Klein bottle, not Torus. So, talking about comparison now, circle versus sphere. The circle and sphere are both compact and connected. However, they have different dimensions and different fundamental groups. So, for the circle, pi one s1 is homomorphic to z integer. For the sphere, it is trivial. Why? On the circle, a loop can wind around the central hole, of the circle, but that winding cannot be removed continuously. On the sphere, every loop can be moved over the surface and contracted to a point, so we can move it around for sphere. Thus, the sphere has no one-dimensional hole in the sense detected by the fundamental group. Then we have the comparison now between torus versus sphere. Both sphere and torus are compact, connected, boundaryless, orientable, and two-dimensional manifolds. Yet they are not homeomorphic. The fundamental groups reveal the difference. So for a sphere, it is trivial, whereas for a torus, it's a two-dimensional integer system. That's z by z. So the torus has two independent directions in which loops can wind. So if you remember the idea of a torus, it's like a tire tube. So you can move around one edge of the tire and you can move around the whole tire. So you have the meridional movement, and then you have the longitudinal movements that way. So the sphere has none for sure. Therefore, no continuous deformation can transform a torus into a sphere without cutting or gluing like that. So we compare again cylinder versus Mobius strip. The cylinder and Mobius strip both have dimension 2, one circular direction, boundary, compactness, connectedness, but they differ in orientability. The cylinder is orientable, the Mobius strip is not orientable. Therefore, they cannot be homeomorphic. The difference arises from the way the two ends of the original rectangle are joined. So for cylinder, the joining is end to end. With the Mobius strip, the joining is also end to end with reversed orientation. That single half twist changes the topology like that. If not, they would have So a Mobius strip would have easily looked like a cylinder, but that twist just changes that idea. So we have a comprehensive plot to plot the several famous spaces that, apart from what I showed initially. So I mean, we've seen these formulas. So for sphere, you go something like this. Yeah, you declare UV, then you have the UV, and you put them into the sine and cosine stuff. Then you have the torus this way. You have the torus that will based on the definition. You need a big R and a small r. You have the Mobius strip, represented by all this. And you have the cone, or the cone coming this way. So by the time you run this now, you get all the famous spaces in one place. So you have your sphere here, you have the torus here, you have the Mobius strip here, you have the cone like that. Um, So, what these spaces teach us, what do these spaces actually teach us? The eight spaces studied in this lesson illustrate several central ideas. The circle introduces winding and a fundamental group. Sphere provides a basic example of a simply connected closed surface. Torus introduces multiple independent non-contractible loops. And Mobius strip provides the simplest important example of a non-orientable surface with boundary. Klein shows how a closed non-orientable surface can arise through edge identification. Projective plane demonstrates quotient spaces and antipodal identification. Cylinder provides a basic surface with boundary and illustrates product spaces. Cone shows how collapsing a boundary can create a new space and produce a contractible object. Together, these spaces form a fundamental library of examples for topology. So, a unifying view, talking about cutting and gluing now. Many famous spaces can be constructed by cutting and gluing simple pieces. So, I mean, cutting and gluing can create new spaces, but I mean, that'll be deformation that is not topological in that case. So for a cylinder, you can start with a rectangle to form a rectangle, right? You can to form a cylinder, you can start with a rectangle and then identify two edges. So you join the two edges together, you can glue the two edges together, and then you have a cylinder. For a Mobius strip, you can start with a rectangle also and identify two opposite edges after reversing orientation. So it's almost like a cylinder, except that instead of joining the edges together directly, you now fold them out and glue like that. So that makes it not quite like a cylinder. Then torus, then you can start with a rectangle and identify both pairs of opposite edges. Then claim but to start with a rectangle and identify one pair in the same direction and the other pair in opposite directions. For projective plane, start with a disk and identify opposite points on its boundary. For a cone, you can start with a disk and collapse its boundary circle to one point. So if I was teaching this in a class setting, this might be like some assignment for people to try out. So these constructions reveal a central philosophy of topology. Complicated spaces can often be understood by starting with simple pieces and specifying how their boundaries are identified. So we have some questions to ask about a topological space. So when encountering a new space, you need to ask, is it connected? Is it path connected? Path connected meaning if you mark any 2 points on the surface, can you connect the 2 points along the surface altogether? Then is it compact? Does it have a boundary? How many boundary components does it have? Is it orientable? What is its dimension? Does it have holes? What is its fundamental group? What are its homology groups? Can it be embedded in R3? Can it be constructed as a quotient of a simpler space? Is it homeomorphic to a familiar space? What happens when we cut it? What happens when we glue its boundaries? These questions turn the study of topology from visual guessing into systematic mathematical analysis. And of course, this is just us trying to be intuitive about the idea of topology. So we have some essential takeaways. The most important ideas from this lesson are, number one, a circle is a fundamental one-dimensional closed space and has fundamental group Z. A sphere is a closed, compact, orientable surface in which every loop can be contracted to a point. A torus has two independent directions of non-contractible loops and fundamental group Z2. A Mobius strip has one boundary component and is non-orientable. A Klein bottle is a compact, closed, non-orientable surface that cannot be embedded in R3 without self-intersection. The projective plane is obtained by identifying antipodal boundary points of a disk, and that's fundamental group Z2. A cylinder, this is 0 raised power 2 here. This is integer 2 like that. That's 0, 1. This is Z by Z. So a cylinder is S1, that's the circle by height, and has two boundary components. A cone is obtained by collapsing one boundary circle to a point and is contractible. So collapse one boundary circle on a cylinder, and leave the other one, and then you get a cone. Most importantly, topology teaches us to classify spaces using properties that survive continuous deformation rather than relying only on their geometric appearance. And that leads us to these practice problems. I think I don't have to bother about this. Just follow what I already said in the notes, and then you should be able to handle some of these questions. Okay, maybe I should show them in fives so you can see questions. Okay, maybe you can see questions 1 to 8 clearly here. Questions 1 to 8 there. Then 9 to 17. You can see 9 to 17 like this. Questions 9 to 17. And the rest. Okay, so let me know how helpful this is for you. And if there's something else you like me to try out, feel very free to let me know. Okay, well, I mean, though I may not solve, I think I can just talk about two of the solutions verbally without solving, because it's not too much of calculations like this. So let's see that. If we consider two questions here, let's say we look at questions 7 and 15. So we've seen everything, but let's see. Question 7 says a surface has no boundary, is compact, connected, and orientable, and has two independent non-contractible loops. Which of the famous spaces in this lesson is the most natural candidate? Justify your answer using a topological invariant. Of course, based on the fact that the surface has no boundary, is compact, connected, and orientable, and has two independent non-contractible. So the most natural candidate, it will be a torus in that case if you match it with the properties we had seen. So the torus is a compact, connected, orientable surface with no boundary. Its most important distinguishing feature is that it contains two independent directions in which loops can wind around the surface. So its fundamental group is pi sub 1 of t squared, which is homeomorphic to z by z, that's integer raised to power 2. So the two copies of z correspond to the two fundamental directions of the torus, one going around the central hole and another going around the whole tube. So this distinguishes the torus from the sphere. Although the sphere is also compact, connected, orientable, and boundaryless, its fundamental group is trivial, like that. So pi 1 of s squared for sphere is equal to E. Therefore, the existence of two independent non-contractible loops identifies the torus as the appropriate space. So the surface is the torus t squared, characterized in particular by pi sub 1 of t squared, which is homomorphic to z squared. That's z by z, talking about integers. Therefore, question 15, if you look at question 15, it says, determine whether the following statement is true or false. If two spaces have the same dimension and the same number of boundary components, then they must be homeomorphic. Give a counter example using two spaces from the lesson. Well, the statement is false. It is not always true that if two spaces have the same dimension and the same number of boundary components, then they must be homomorphic. It is false, because having the same dimension and the same number of boundary components is not sufficient to guarantee that two spaces are homomorphic. A useful counter example is the cylinder and the Mobius strip. All right. Both are two-dimensional surfaces with exactly one or more boundary components. More precisely, the cylinder has two boundary components, while the Mobius strip has one. So they do not provide a counterexample to the statement as written. Instead, consider the circle and another one-dimensional space with no boundary, such as a disjoint union of two circles. Both have dimension 1 and no boundary, but they are not connected in the same way. So the circle S1 is connected, whereas S1 has two connected components. So connectedness is a topological invariant. So no homomorphism can exist between them. Thus, dimension and boundary information alone do not completely determine the topology of a space. So the statement is false. So additional invariants such as connectedness, orientability, compactness, Euler characteristic, and fundamental group may be necessary to distinguish spaces. So it's not enough to just talk about dimension and boundary components alone. So you may need more information to decisively distinguish between spaces. So on that note, thank you so much for listening. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. And shout out to Michael Ikechiku, who inspired me to do this particular playlist on topology. If you have issues with any aspect of mathematics, any level of math at all, you may let me know. I might be able to make a video for you too, like that. On this note, if you have subscribed to this channel, I thank you very much. If you have not subscribed, this is a very good time to go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, which gives you special privileges that you find as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.